Welcome to Module 4, Energy Economics. This is where engineering side of an audit meets the business side. We have spent the last few weeks learning how to count BTUs, megajoules, and read complex utility bills. Today, we move into the boardroom. You will be the board of director making decisions based on economic analysis. In energy auditing, if you can prove the economics, your project doesn't exist. So this is important. We'll go through the basics of payback and dive into the time value of money, the math used by CFOs, the chief financial officers, to decide whether to give you the budget for new boiler or put that money into a, say, high interest saving account. So how do we prove to a building owner that our energy conservation measures are worth the investment? This module covers the math required to turn a technical recommendation into financial one using economic analysis. We use the term compare apple to apple. What if we want to compare apple to orange? Which one should we buy? We perform economic analysis to select the most cost-effective solution among many options. It allows us to compare apple to oranges, like comparing a lighting retrofit to a new roof, right? Let's say if a client has $100,000, they could spend it on your energy project, saving maybe $10,000 per year. Or they could spend it on a new production line, earning $50,000 per year. If your return on investment isn't better than the core business return on investment, you will lose the funding. This is why energy is always competing against growth. Okay. Simple payback is the most popular metric because it is the easiest to understand. How many years until I get my money back, right? So this here, the payback trap. An auditor tells a client, this model pays for itself in 6 months. The clients ask, great, but does it work after those 6 months? Right? The point is, simple payback it ignores everything after the payback date. A cheap LED might have, say, 1 year payback, right? Because it's cheap, it's easy to get the money back. But it dies in year 2. And compared with a high quality LED might have 2-year payback, but it lasts 10 years. So under simple payback, the cheap one looks better, which is technically wrong for the client's wealth in general. Okay, so simple payback is simply the initial cost divided by the annual savings and how many years you can get the money back. That's a definition for simple payback. The advantage is that it's easy to apply, very straightforward, simple formula. So it's quick, simple to calculate, no complex financial models. Also, no assumptions for future factor required. It relies only on the current utility rate and the annual savings, right? Avoiding uncertainties about future energy costs or inflation. As well, the operating costs are not required. Make it, again, simple to calculate. However, the disadvantage though, because it ignores saving beyond the payback period. Therefore, it fails to recognize long-term financial benefits after the investment has paid for itself, meaning after the payback date. And that can lead to undervalue the energy conservation measures with high long lifetime savings. It also misses the impact of future change in economic factors, right? It doesn't account for the increase in energy cost. It doesn't account for the inflation, right? We know the inflation is giving a lot of pressure these days, and other variables that may affect savings or costs. It also favors projects with high initial savings relative to installation cost. The cheap LED example we have compared to a more better quality that lasts longer LED that we have. Yes, the cheaper one, we can quickly recoup the initial investment, but if the better quality one, it takes a bit longer to get the money back, but after that it lasts longer, and therefore the benefit lasts longer. Okay, so these are the pros and cons of a simple payback method. Let's look at this lighting retrofit example. We are cutting wattage from 46 watts to 30 watts. 46 from the 2 compact fluorescent per fixture luminaires, right? So 23 times 2, 46 to 30 watts. Because if we replace compact fluorescent lamp with LED, and it's 15 watts each, so per luminaire it's 15 watts times 2, so 46 to 30 watts. Now it costs $5 per LED lamp, right? So that's the cost. Runtime, it tells us how long the lighting system operates. Monday to Friday is 7 o'clock to 6 p.m. and that would be 11 hours during the weekday, and on Saturday 9 to 1, 4 hours on Saturday, nothing on Sunday. The utility rate is 10 cents per kilowatt hour used. So this is usage. $9 per kilowatt, this accounts the peak demand cost. So if the lighting system operates during the peak demand, then we need to include $9 per kilowatt. If the lighting system is turned off during the peak demand, then this $9 does not apply. Okay, so now determine the project payback. How long does this project pay back? Let's do the calculations. So first, let's do the initial cost. How do we find the initial cost? Well, we have 1,000 fixtures. Well, you can see 1,000 fixtures. And 2 lamps per fixture. $5 per lamp. Okay. So what's the cost? Lamp, fixture, dollar amount. So 10, 1,000, 10,000. So the initial cost is 10,000. How about energy savings? energy savings. First, it's compact fluorescent lamp, 23 watt each. We are replacing them with LED lamp, 15 watt each. So we can say 23 watt times 2 minus 15 watt times 2. That's the difference. You get 16 watt of saving per luminaire. Okay. So the consumption savings. That's how much the LED, if we replace the compact fluorescent with LED, consumption savings. That's equal to 16 watts, and we have 1,000 luminaires or fixtures. Here we say fixture. The technical term is luminaires, right? So total, it gives us 16,000 watts of saving. Now, how long is the operating hours? 55 during the weekday and 4 hours during the weekend. So total 59 hours per week. Okay, 59 hours per week and 52 weeks per year. Okay, 52 weeks per year. The savings multiplied by 10 cents per kilowatt hour. Now let's check the unit. I have a fixture here. So this is 16 watts per fixture. I forgot about to write that. So fixture and fixture. Week and week. We want to save in per year, so it's there. The hours cancel out just this kilowatt hour, right? This kilowatt hour right here, and the hours. So we still have dollar per hour, and kilowatt. Now be careful. Here is 16 watts. We have kilowatt here. So let's replace this kilo by 1,000. And then therefore we can cancel this 1,000, here 1,000. Okay, but don't forget about, and then this watt and watt. So what I'm doing is that I'm checking my unit, see if everything's consistent. So now we only have the numbers and the dollar sign per year, right? Dollar sign per year, that's it. So let's do the calculation here. What's 16 times 59 times 52 multiplied by $0.1 or 10 cents? So the number I have here is, again, check the math, $4,908 and 80 cents. Okay, per year. The peak demand savings. That's how much the lighting use increase the peak demand, and therefore we have to pay $9 per kilowatt. Okay, and this is billed monthly, right? It's billed. You can say see monthly billings right there, monthly billing. So 16 watts per fixture times 1,000 fixture times $9 per kilowatt, and don't forget per month as well, times 12 months per year. Let's check the unit again. This kilowatt, so I have a 1,000 here. This 1,000 cancel. This fixture cancel. The watt cancel. And the month cancel. Right? So now we have $sign per year again. So that's equal to the number I have. It's $1,728 per year. Okay, oops, my dollars. Okay, this per year, right? Per year. So total saving. Where can I write? Let me write here. Okay, total savings is equal to 1,728 and the $4,908.80. The total, both of them, equal to 6,636.8. Per year. So what would be the payback? What would be the payback? Well, the initial cost is right here. 10,000. So 10,000 divided by that number. That should give you about around 1.5. Around 1.5. So less than 2 years, right? We get the money back. You can tell me about it when we meet. Okay. So this example here, right? It tells us this tells us that when you save energy matters as much as how much, because of that peak demand. Okay, because of that peak demand. Next, the time value of money in energy retrofit project. Why is time value of money important? Well, energy retrofit projects often involve significant upfront costs and recurring savings over the equipment's life. By applying the time value of money, you can accurately compare the value of money invested today to future savings. Okay, because $1 today is not equal to $1 tomorrow, right? Second, make informed decisions, right? This time value of money, you can make informed decisions about whether a project is worth the investment. Also, you can prioritize projects with higher returns or shorter payback when budgets are limited. You cannot do everything. There's so much we want to do. We only have 24 hours a day, and similarly, we have limited amount of money to spend. Cash flow diagrams. What are they? Cash flow diagrams are graphical representations that illustrate the inflow or income and outflow expenses of capital during the lifespan of an energy efficiency investment. They help visualize initial investment, basically the upfront cost of the project, the ongoing savings, for example, operational savings or revenues generated from the investment. The, the life cycle cost, right? The maintenance, operating expenses or replacement cost over time. Also the final salvage values, any residual values of equipment at the end of their life, right? It also can be shown on the cash flow diagram. So let's take a look at a cash flow diagram. The story here is, let's say it's a pilot energy retrofit project. A building owner runs a 4-year pilot retrofit project to test new energy savings control before a full rollout, right? So year 0, no cash flow, that's nothing for year 0. And the time used for planning, approval, baseline measurement, just doing some preparation work. And let's say there's no financial investment, right? Just time spent. The first year, now you implement that's the implementation cost, and that's say 35, whatever that unit is, make it billions if you like, right? But 35 units, no income because it's just the project is implemented. What happened? The owner purchased and installed new control hardware, sensors, pays for commissioning and staff training, so on and so forth. So the system is not yet optimized, so there are no measurable savings in the first year, okay, in the first year. So a lot of upfront cost, right, in year 1. Year 2, there's some benefit begin to surface. So you start to see some income now. And let's say it's 10 units. No expense because all the money has been already spent in year 1. No expense for the second year. What happened? Well, after a year of operation and tuning, the system start to producing modest energy savings. No major maintenance or upgrades are required, right, for that year. Okay. Year number 3, performance improvement with maybe minor cost. And let's say the income is 15. You can see income 15. The red bar, that's 15. The yellow bar, there's some expense, right? But the net gain is still 10 units. And perhaps additional optimization and control strategy refinement increase the energy savings. But there's a little small expense, right? You always have to spend a little bit, just like maintaining our house. So a small expense occur due to sensors replacement, software update, things like that. Year number 4, the final year of the pilot project, the operation has been matured. It's with operating costs. You know what's going to happen, how much you spend, how much you can save. And let's say this year income 15, expense 10. You still have net 5 unit, positive 5 unit net gain, right? The system is now fully optimized, continue to generate strong savings, but higher operating and maintenance costs appear as components become older, need replacement, service contract kicks in, stuff like that. So based on this scenario, you will see upfront cost, some savings in year 2, 3, and 4, and a little bit of maintenance, upgrade costs in 3 and 4. Right, that's what's called cash flow diagram. When you look at the net cash flow over the 4 years, really there should be a 0, 1, like should be a 0, 1 here, but because it's 0, 0, it's not shown. But when you look at the cash flow of 4 years, this project is not very attractive on its own. The upfront cost is large and the savings arrive late and are partly offset by operating costs, right? However, this does not mean the project is fundamentally bad. If you extend the analysis to, say, 5 or 10 years, the continued savings could eventually make the project net positive. Okay, net positive. Now, at a save on energy rebate, let's say there's a rebate, right? That rebate does not reduce the initial cost, but because that incentive, it can, let me say that again. The initial cost is not reduced, but because of the rebate, it can offset the initial cost, making the whole project much more attractive, right? Significantly reduce the payback period. Okay. So you can consider rebate as income, and rebate, they are almost always paid after verification. So they usually appear later, say maybe year 2, right? In year 2, the rebate doesn't improve the engineering performance of the system, but it improves the short-term cash flow, right? It makes the project much more attractive early on, and can ju justify proceeding before the long-term benefit fully accumulate. Okay, fully accumulate. The key, the key lesson here is that engineering economics, when money occurs, is just as important as how much, right? The when, it's very important. Year 1 or year 4, big difference. Now, we have seen an example of a cash flow diagram and how timing affects project attractiveness. The next step is to evaluate this cash flow systematically. Okay, systematically. The engineering economics give us evaluation method like net present value, future worth, and annual worth. These tools allow us to account for the time, again, the time value of money. Right? It ties time into the value of money. Compare cost and benefit across years, and make informed decision about whether a project is economically viable. Now let's look at each method and see how it applies to our example. Net present value. Okay, present value, that's the gold standard. It tells us if a project actually creates wealth after accounting for the cost of money. What does that mean, cost of money? Well, future value is present value multiplied by 1 plus discount rate. If it's 1 year, n equal to 1. If for 2 years, n equal to 2. And this equation is saying, for example, if I have $1 today, that's the present value. If I put this $1 into bank, that gives me interest of, say, 2 or 3%, and that's pretty good these days. Let's say 2%. Then next year at the same time, I will get $1 times 1.02 to the power of 1. So basically, the future value of this $1 in 1 year, it's $1.02. Okay, we'll look at that. Similarly, I should mention that, similarly, if you use credit card, and that's, of course, if you use credit card, it charge, if you pay on time, no problem. If you don't, what happens? Well, the interest will accumulate, right? So the dollar you spend right now, and if there's an interest, whatever that interest, 10, 20, even 30%, right? Then in the future, you will need to pay, let's say 10%, even just 10%. $1 today, 10%, 1.1 in 1 year. This $1 becomes $1.10, the future value. Okay, so think about it. Net present value, NPV, sometimes we short for NPV, allows us to compare the original investment to the net income it generates over time. Basically, it tells us whether spending money today is worth it when we consider all the future cash flows. For a project like installing energy saving equipment, we calculate the net present value over the life of the system, the whole life of the system. If the net present value is positive, it means the project will increase wealth. The net present value of all future savings and the benefit is greater than the initial cost. And that's only when net present value is positive. If it's negative, the project reduces wealth. So it wouldn't be a good financial decision. Net present value gives us a clear quantitative way to evaluate project and decide which one worth pursuing. Right? Or if you compare two projects, which one has the higher net present value? That's a better project. So here are the steps for determining net present value. You convert all the expenses and incomes, basically the cash flow diagram that we saw earlier, right? You have income and expenses. The cash flow amount over the whole lifetime of the project to a present value. Sum the present value, include the initial investment, and then determine if the net present value is positive. Okay, so we saw that equation a few slides ago. Let me show you again. Future value is equal to present value multiplied by 1 plus discount rate to the power of n. And that n is how many years? The number of years. Now to the future, right? Here, it's the same. Present value equal to present value. It's simple, like just makes sense. It is what it is right now. But in 1 year, that present value becomes the future, the F1, it will worth this much after 1 year. How do we calculate that? PV plus the discount rate times PV. And if you take the PV out, right, it's PV times 1 plus R. If you notice, it doesn't have an N because, well, N equal to 1 in this case. Okay. In 2 years, the future value of F1 is equal to F1 plus the interest it generates, so R times F1. But what's F1? If you replace F1, it's actually PV times 1 plus R. And then that F1 times R, so you have another 1 plus R. So really it's PV, present value, multiplied by 1 plus R, now to the power of 2, because you have 2 of them. You have 2 of them. And that's N equal to 2, because it's the value after 2 years. And of course, so on. The value after n years, Fn, is PV multiplied by 1 plus R bracket to the power of n. this is a general expression.